So, okay, I was saying congratulations to the organizers for this online conference, and thank you for allowing me to talk about these new instruments to measure the first-ray mobility. Okay, in daily clinical practice, we are constantly measuring. We are constantly measuring mobility, measuring temperature, measuring pressure, etc. And we need to use instruments to make those measurements. Those instruments have to be valid and reliable. And it would be better if they are also easy to use, simple, lightweight, etc. We are surrounded by the instruments that meet these requirements when used correctly, and they allow us to make lots of procedures and measurements. But what about the measurement of the first ray mobility? Because of its axis orientation, the first ray has motion in the sagittal and frontal planes at the same time. So these instruments are not useful to measure the first ray mobility. For years, some authors have developed different types of devices. Roger and Kavanagh built the first device in 1986. Here we can see that it was a complex structure. Clough and colleagues built an instrument that was validated, but it is not available for acquisition currently. The Glasgow device is one of the most used in research, but it is also a bit complex. And there also exist some others that are less complicated, but their validity and reliability has not been sufficiently demonstrated yet, as this one by Kim and colleagues, Witness, or Michaud. And that was the reason why we wanted to design and build a simple, easy to use new instrument to measure the first ray motion. We started with our idea on a paper sheet, and then it started to take shape, but realized that it was being similar to others and decided to incorporate something different that really reflected the true motion of the first metatarsal head. So we incorporated this curvature, okay, so that the instrument reflected the motion of the first metatarsal head in the sagittal and frontal planes at the same time. And this idea was patented, okay. We contacted a design engineer to start the manufacture by 3D printing, and he started the computer-aided design, okay. Everything was going okay until he made an important question. He said, how exactly is this curvature? Is it a circumference arc? Is it an irregular arc? And we said, we don't know. And he told us, you must know. So the first thing we had to do was to define an adequate curvature for the new instrument. For this, we obtained, in a first study, we obtained 3 anterior-posterior radiographs from 36 participants who had normal first ray. One of the radiographs with the first ray in neutral position, another one with the first ray maximally dorsiflexed, and the other one with the first ray maximally plantar flexed. Here we can see an example of the 3 images, and 3 points were identified. One point on the tip of the medial malleolus that was used as a fixed point. Another point, point 1, on the intersesamoid crest, and the last point on the superior medial tubercle, where the medial collateral ligament of the first metatarsophalangeal joint begins. To record the first ray motion in the sagittal plane, the distance from points A to point 1 was recorded in the 3 positions, and the difference between them was calculated. To measure the first ray motion in the frontal plane, in the 3 positions, an angle formed between the following 2 lines were drawn. One line joining the points 1 and 2, and the other line was a horizontal line parallel to the ground. When this angle increased, the mobility was recorded as inversion, and when this angle decreased, the mobility was recorded as eversion. Using these measurements, the engineer was able to obtain a curve of first ray mobility of each participant, and using these curves was able to obtain an average curve of motion that was used to definitely design the instrument. This is the curve. Also, the horizontal arms had to be well fitted to the dorsal surface of the foot. So using a profiler, we obtained the shape of several feet on the dorsal surface, and the horizontal arms were fitted in a better way after several pilot tests. Here we can see the evolution of the horizontal arms as well. Okay, and here we are going to see a video explaining. Explaining how to use the longest horizontal arms on the 3 metatarsal, lesser metatarsal, the shortest horizontal arm on the first metatarsal head, and the vertical arms on the second metatarsal neck. So we take the first metatarsal to the initial position, look at the max, and push it to the maximal dorsiflexion, and then we count how many marks has it moved, and the same to the maximal plantar flexion. Okay. Once the instrument was designed and built, what we had to do now was to check whether this instrument was valid. That is, whether it measured what we really wanted to measure, and also to check whether it was reliable. That is, whether it provided the same results when used to measure the same foot by several times by different examiners. In order to validate the new device, dorsal flexion and plantar flexion obtained from X-ray images and those obtained from manually with the device were compared in normal and hallux valgus feet. The cluster analysis reported good results, as the silhouette measure of cohesion and separation coefficient was always higher than 0.5, which means a good classifications. The Bland-Aulman graph also showed an excellent agreement between the different measurements, X-ray and manually with the device, as 96% of the data showed agreement between both measurement methods. And the rock analysis also provided good results, as positive and negative predictive values were over 60%. So with this data, we can say that the new device is valid. And in order to determine the intra and inter-examiner reliability, this measurement protocol was done twice on all the participants by two different researchers in another study, 25 normal fit and 24 hallux valgus fit. Each measurement by the same examiner was separated by a period between 10 and 30 days. And here we have the values of the intra-class correlation coefficient. We can see that they are near 1. So both the intra-observer and inter-observer reliability was good. And so with this data, we can say that the new device showed a good reliability. So to conclude, a new device to measure the first ray motion in daily clinical practice has been presented. It has characteristics that make it possible to be used every day in our clinical practice, because it is a simple, lightweight, small, portable, and easy to use instrument. And it is valid and reliable. The statistical analysis suggested that it showed a good validity, as it correctly classified 96% of the participants and provided good concordance with X-ray measurements. And lastly, it showed excellent intra and inter-examiner reliability. So now we have lots of possibilities to do research related to the first ray using this new instrument. Thank you very much for your attention.